SpaceX just caught a 233-foot booster using mechanical arms on a launch tower. The booster weighs over 200 tons and carries 33 Raptor engines. Each engine costs around $1 million. But here's what most people missed. SpaceX isn't just catching the booster anymore. They're building a tower system that catches both the booster and the upper stage. Why does that matter? Because every Starship stack costs $120 million in hardware. Without this tower solution, that entire rocket gets thrown away after one flight. Let's dive right in. To understand why this tower is such a breakthrough, we need to look at what rocket launches used to cost. For decades, the aerospace industry accepted one brutal fact. You build a rocket, you fly it once, and then you watch millions of dollars sink into the ocean or burn up in the atmosphere. Take the Saturn V. This was the rocket that sent humans to the moon. Standing 110 meters tall, it remains the most powerful rocket ever flown. Every Saturn V launch cost between $1.2 and $1.5 billion in today's money. The first stage alone used 5 F1 engines. Each engine weighed 8.4 tons and produced 690 tons of thrust. After launch, all 5 fell into the Atlantic Ocean. Never recovered, never reused, just gone. And this wasn't seen as wasteful at the time. This was just how rockets worked. But here's the question nobody was asking back then. What if you didn't have to throw away the most expensive part of the rocket every single time? SpaceX started answering that question with Falcon 9. In 2015, they landed their first booster. People thought it was a one-time stunt. Today, Falcon 9 boosters have flown up to 19 times. Landing on drone ships in the middle of the ocean became routine. The industry changed overnight. But even with Falcon 9's success, there was still a problem. The drone ship method works, but it has limitations. You need recovery vessels. You need ocean operations. You need time to transport the booster back to land. And you're still only recovering one stage. Starship operates on a completely different scale. The Super Heavy booster stands 71 meters tall and uses 33 Raptor engines. At liftoff, those engines generate 7,600 metric tons of thrust. That's more than twice what Saturn V produced. Each Raptor is a full-flow stage combustion engine, one of the most complex rocket engines ever built. Now think about this. If SpaceX threw away 33 Raptors after every flight, how sustainable would that be? This is where the Mechazilla tower changes everything. Instead of landing on legs or aiming for a drone ship, Super Heavy comes straight back to the launch site. After stage separation at around 65 to 70 kilometers altitude, the booster performs a boost-back burn, re-enters the atmosphere, and uses grid fins to control its descent. In the final seconds, it relights engines to slow down and approaches the tower at nearly zero horizontal velocity. At this point, the booster still weighs over 200 tons. The tower's mechanical arms catch it mid-air, using load-bearing pins mounted on the vehicle. No landing legs, no ocean recovery. The booster goes from space back to the launch mount in under 10 minutes. But SpaceX isn't stopping there. They're planning to catch the upper stage too. This is where it gets really interesting. The Starship upper stage is 50 meters tall and 9 meters in diameter. After reaching orbit at around 250 to 300 kilometers altitude, it's traveling at 7.8 kilometers per second. That's over 28,000 kilometers per hour. During re-entry, surface temperatures exceed 1,400 degrees Celsius. After atmospheric drag removes most of that energy, Starship performs a powered descent. Even with nearly empty tanks, the dry mass is still over 100 tons. The plan is to catch the ship using the same tower that caught the booster. But there's a timing challenge here. How do you use one tower to catch 2 different vehicles? Here's how SpaceX solved it. The booster gets caught first within minutes after launch. Once Super Heavy is secured, it gets lowered onto the launch mount or moved using the tower's carriage system. This takes tens of minutes, not hours. Meanwhile, Starship is still in orbit. The upper stage doesn't return immediately. It completes at least one full orbit around Earth before coming back. That means the ship returns 90 minutes or more after launch. This time gap is crucial. Ground crews have enough margin to reposition hardware and reconfigure the tower for ship recovery. The tower essentially serves double duty on every flight. First catch, booster. Second catch, ship. Both stages recovered at the same launch site. This is why SpaceX is investing heavily in tower upgrades and building specialized chopstick systems optimized for each vehicle type. Now let's talk about what this actually saves. The numbers are staggering. A full Starship stack flies with 39 Raptor engines total, 33 on Super Heavy, 6 on the upper stage. At roughly $1 million per engine, that's $39 million in engines alone. But that's just the beginning. The Super Heavy booster is a massive 71-meter structure made from thick stainless steel. It includes propellant tanks, avionics, grid fins, actuators, plumbing, and structural reinforcement. Even without engines, a single Super Heavy booster is estimated at $40 to $50 million. The Starship upper stage adds another $30 to $40 million. When you add it all up, one fully expendable Starship launch throws away roughly $120 million in hardware. Now watch what happens when you recover instead of destroy. 5 recovered flights? That's $600 million saved. 10 flights? $1.2 billion. 20 flights? $2.4 billion. The savings scale exponentially because you're not rebuilding rockets from scratch every time. But here's what makes this tower solution truly brilliant. It's not just about saving money on hardware. It's about changing the fundamental economics of space access. Traditional expendable rockets forced a simple equation. Every launch costs roughly the same because you're always building a new rocket. With full reusability, that equation breaks. Your per-flight costs drop to propellant, operations, and maintenance. The hardware becomes capital investment, not operational expense. Think about commercial aviation. Airlines don't throw away a 747 after every flight from New York to London. They refuel it, perform maintenance checks, and fly it again. That's why air travel became affordable and frequent. SpaceX is applying the same principle to rockets. The tower is the infrastructure that makes it work at scale. The Starbase launch tower stands roughly 146 meters tall. The chopsticks ride on rails, allowing vertical movement across most of that height. These systems are engineered to handle vehicles weighing well over 100 tons while absorbing dynamic loads during capture. The tower isn't just infrastructure anymore. It's part of the flight system itself. It has to survive the forces of launch, support propellant connections, and execute precision catches on returning vehicles. This is why the tower represents such a critical breakthrough. Without it, Starship would need landing legs on both stages. Landing legs add weight. Weight reduces payload capacity. Payload capacity is what you're selling to customers. By eliminating legs and using the tower instead, SpaceX maximizes what Starship can carry to orbit while still achieving full reusability. The tower does the heavy lifting, literally. So here's what SpaceX actually built. It's not just a launch tower. It's a recovery system that turns a $120 million single-use rocket into a reusable spacecraft. Every time those mechanical arms catch a booster, SpaceX saves 33 Raptor engines worth $33 million. Every time they prepare to catch the upper stage, they're protecting another $87 million in hardware. But the real breakthrough isn't the money saved on one flight. It's what happens when you stop throwing away rockets altogether. For 60 years, space access was limited because rockets were disposable. You couldn't fly often because you couldn't afford to keep building new ones. SpaceX's Tower Solution breaks that cycle. The same Starship stack that launches today can launch again next week, and the week after that, and the week after that. This is how you get from a few launches per year to hundreds. This is how space becomes accessible. The tower standing at Starbase right now is just the beginning. SpaceX is already developing upgraded versions for Starship Block 3. More capacity, faster turnaround, higher reliability, because once you prove the concept works, you optimize it. And that's exactly where we are now. What SpaceX demonstrated wasn't just catching a rocket. They proved that full reusability at orbital scale is achievable. The tower is the key that unlocks everything else. If you want to stay updated on Starship's development and SpaceX's next breakthroughs, subscribe to Space Update 24 Hours. Hit that like button if this breakdown was valuable. Drop a comment with your thoughts on what SpaceX should tackle next. And share this with anyone who still thinks reusable rockets are science fiction. Rice dumplings, pork chops, braised quail eggs. China's astronauts eat real food 400 kilometers above Earth. Tiangong has 120 plus food types, a 10-year microwave, and crews who eat tea with chopsticks in zero gravity. How did they solve space dining? The dining area has a food heater, fridge, water supplies, and folding tables. What makes cooking work in orbit? Let's dive right in. The space microwave arrived on the Tiangong 2 cargo craft, and it's not your kitchen appliance. This device survived launch vibrations that would destroy normal electronics. Built with a high-efficiency magnetron and custom lightweight power system, it operates continuously for 10 years without maintenance. Why does a microwave matter so much? Because warm food changes everything about living 400 kilometers from home. Breakfast starts with porridge, bread, pickled radish, or braised quail eggs. Lunch brings fried rice, pork chops, potatoes, and beef soup. Dinner features tuna, mushrooms, and lettuce, with chocolate and fruit for snacks. The Tiangong core module stocks all 120 food types in a dining area equipped with a food heater, refrigerator, drinking water supplies, and folding tables designed for microgravity. But here's what makes this remarkable. The space refrigerator does double duty. It preserves meals and maintains research samples at stable low temperatures for scientific experiments. The ISS has the cold atom lab that chills atoms to nearly absolute zero at minus 273.15 degrees Celsius to study quantum effects. Tiangong's fridge supports similar critical research while keeping astronauts fed. Then there's tea. In microgravity, liquids don't pour. They form floating droplets. Chinese astronauts eat their tea with chopsticks, using surface tension to grab the droplets midair. What other century-old traditions work in zero gravity? Water tells a different story. There's a saying on the ISS, yesterday's coffee is tomorrow's coffee. It's reality, not humor. Both stations recycle water from sweat, breath, and urine through condensation, distillation, purification, and filtration. The ISS recovers 95% of its water. Tiangong achieves 90%. When every kilogram costs thousands to launch, that 5% difference matters less than you'd think. Both systems turn waste into survival. Bathing without showers requires creativity. Astronauts warm wet towels to wipe their bodies. For hair, they wear shower caps and rub in rinse-free shampoo. The station has a wrapped shower area where crews rinse with spray guns and wipe clean. It's functional hygiene, not luxury, but it works for months at a time. Sleep reveals Tiangong's smartest design choice. Each taikonaut gets a private cabin about the size of a twin bed with standing headroom. Privacy, real privacy. The ISS crams astronauts into phone booth-sized pods. Why did China prioritize personal space?